Background literature. Software tools support knowledge engineers in the difficult task of knowledge acquisition and ontology construction. From a survey of research work on ontology tools, we found the existing tools do not provide adequate support in 5 areas, which include, Harrison and Chan, 2005, 1. Support for an ontological engineering methodology, 2. Support for dynamic knowledge modeling, 3. Support for dynamic knowledge testing, 4. Support for ontology visualization, and 5. Support for ontology management. They are discussed in detail as follows. Most of the examined tools were not developed based on an ontological engineering methodology, which can help expedite the ontological engineering process. The methodology provides a sequence of steps, procedure or guidelines that help developers in the process of constructing an ontology. Some examples of research works on tool support for ontological engineering methodologies include OntoEdit, which supports ontoknowledge, Finsel et al., 2002, WebOde, which supports methontology, WebOde, and Knowledge Modeling System, KMS, which supports the inferential modeling technique, INT, Chan, 2004. While a primary function of a tool that supports ontology construction is its ability to model the problem domain, most tools only model static domain knowledge about classes and attributes but ignore dynamic knowledge, which refers to the knowledge about objectives, tasks and activities, Chan, 2004. A brief survey of the different ontological engineering support tools reveal there are diverse methods employed. For example, the method used by Protégé, Ontolingua, and Ontobuilder, for modeling ontologies is to use a hierarchical tree listing all the concepts, and input fields are provided to capture characteristics of concepts. A graphical method of modeling ontologies is employed in tools such as K-ON, KNO, and Protégé Alvas plugin, Protégé Alvas, in which the representational method involves nodes to represent concepts and edges to represent relationships between concepts. A different approach is adopted in the Unified Modeling Language, UML, tools, which are commonly used to visually describe and communicate the design of software. Due to the similarities between ontologies and object-oriented design, UML class diagrams can be used to model ontology classes and their properties, and relationships between classes, Cranfield et al., 2005. However, UML's expressiveness for modeling ontologies is limited, and standard UML cannot express more advanced ontologies that contain descriptive logic, Jurich et al., 2005. Due to the limitations of UML, there is ongoing work to develop a graphical notation for ontologies, called the Ontology Definition Metamodel, ODM, Jurich et al., 2005. The existing tools described can model static knowledge to varying degrees, but they often lack the facilities for modeling dynamic knowledge. For example, it is awkward to link a task to an objective in Protégé using the existing input fields. This is a weakness that our research addresses. The examined tools that support ontology construction do not include facilities for supporting ontology testing. Analogous to software testing, which identifies defects during development and results in a more stable software application being constructed, ontology testing can help the knowledge engineer develop a more complete model of the domain. In the ontological engineering field, ontology testing is also called ontology evaluation. According to Gomez-Perez et al., 2005, ontology evaluation should be performed on the following items. Every individual definition and axiom. Collections of definitions and axioms stated explicitly in the ontology. Definitions imported from other ontologies. Definitions that can be inferred from other definitions. Existing ontology testing systems, such as the OWL Unit Test Framework, OWL Unit Test Framework, and Chimeras, MC Guinness et al., 2000, Test Suite, evaluate the correctness and completeness of ontologies. Chimera performs tests in the following 4 areas: 1. Missing argument names, documentation, constraints, etc. 2. Syntactic analysis, for example occurrence of words, possible acronym expansion. 3. Taxonomic analysis, for example unnecessary superclasses and types, and 4. Semantic evaluation, for example slot/type mismatch, class definition cycle, domain/range mismatch, MC Guinness et al., 2000. Such testing tools are sufficient for testing static knowledge, but are not suitable for testing the interactions between behavior and objects. Our research work aims to fill this gap in research by addressing the difficult issue of testing behavior or dynamic knowledge. Our approach attempts to combine unit testing techniques with the adoption of test cases in test-driven development, TDD, Jansen and Saadian, 2005. This is a useful hybrid approach for addressing the complex interactions of task behavior and objects. The general intuition adopted from the TDD approach of testing is that it should be done early and done often. In TDD, a test case is written first and then the actual module is written. Writing test cases first can be beneficial because instead of thinking of test cases as how do I break something, writing test cases first make you think what do I want the program to do. In other words, writing test cases first make you think about what functionality and objects are required. Ontology development could also benefit from this kind of approach. Most ontology editing tools lack visualization support. Often ontology visualization tools use two-dimensional on 2D graphics for representing concepts and relationships among concepts. 2D graphics are often employed for representing static knowledge in hierarchical or frame-like structures. However, 2D graphics are not adequate for representing complex and related information because there is insufficient space on a bidimensional plane, where complex and related visual objects tend to squeeze together or even overlap with each other. In an effort to accommodate a model of complex related objects in a 2D plane, existing visualization tools either collapse lower priority visual objects into high-level objects, or implement different representations that offer multi-perspectives on an organization of knowledge elements. While these approaches solve the problem of related objects being overcrowded in a shared space, it sacrifices clarity of the display. A popular ontology editor is Protégé, which has some degree of visualization capabilities in that it generates a tree view of classes. The Protégé's ontology visualization applications are implemented in its plugins. Some examples of these ontology visualization plugins include Jambalaya, Wuan Story, 2000, and Ontosphere, Bosca et al., 2005, which are discussed as follows. Jambalaya is an ontology visualization tool plugin in Protégé. It provides several viewing perspectives for the ontology model, thereby enhancing user browsing, exploring and interacting with the 2D ontology visualization. Jambalaya only visualizes the static knowledge of classes and instances of an application ontology, it does not support dynamic knowledge visualization. Furthermore, since Jambalaya is based on 2D graphics, the space it supports is insufficient for rendering complex knowledge. In its representation, text labels and symbols tend to overlap when the domain ontology is represented as a hierarchy involving many levels of concepts. This deficiency means it is difficult for users to view and understand the concepts and the relationships among concepts when the domain ontology is complex. Ontosphere is also a Protégé plugin. By employing 3D graphics for visualization, Ontosphere extends the volume of space available for visualizing overcrowded concepts. The three-dimensional or 3D view is natural for humans. And its main advantage is that it allows users to manipulate the visualized knowledge elements of the application ontology by means of the actions of zooming, rotating and translating. Through physical manipulation of the concepts, the user can better understand a complex ontology. For this purpose, Ontosphere provides 4 scenes so that the user can observe a visualized application ontology from multiple perspectives. However, the weakness of Ontosphere include, 1. It was not developed based on any ontological engineering methodology, and, 2. It does not support visualization of dynamic knowledge. Although the employment of 3D graphics enlarges the space available for rendering images, the problem of overlapping concepts and labels still exists when the application ontology is complex. Currently, ontology development within the SW is not managed in a systematic manner. Anyone can create, reuse, and/or extend concepts in a distributed and heterogeneous environment, and different versions of an ontology can be created, which results in backwards compatibility problems. A system for ontology management is needed in order to document, track, and distribute ontologies in such an environment. Existing ontology management frameworks provide inadequate support for replicating an ontology within the public domain and detecting when a public domain ontology has been tampered with. In addition, Weaknesses of existing ontology management systems include vulnerability to malicious ontology authors, little consideration for intellectual property rights, and lack of support for ontology versioning.